Welcome back. We're going to jump right in. And as I alluded to in the last lecture video is how do we deal with drawing large structures? Just to kind of show a little example of this, like we can draw the Lewis structure here. This is a compound um, known as methane, and we can draw that really quickly. Let's add another structure to it or another carbon to it. And we can draw the Lewis structure, again, showing all the bonds, all the electrons, and this is something that's known as ethane. All right, great. That didn't take much time. Well, let's do something else, and that's add another carbon. And we'll do the Lewis structure for that. Okay, so that takes a little bit longer and so on. But I want you to imagine for a second, if I asked you to draw the Lewis structure for an organic compound that had 100 carbons in it and 200 hydrogens, you would be spending an obscene amount of time drawing out every single carbon, every single bond, and every single hydrogen. So we have a little bit of a better system, a better type of formula that we can use that will make this a lot simpler for drawing large molecules. And we call these line angle formulas, or also known as skeleton formulas. And what we do is we use lines to represent the same information, the same information as a Lewis structure. So if we were to look at the structure here of propane and make that Lewis structure into a line angle formula, this is what it would look like. You say, okay, I don't see any atoms. Like, what is that supposed to mean? So wherever two lines meet, that represents a carbon. And wherever lines end, that represents a carbon. So this carbon here is this one on the end. Actually, I'm going to use a different color. This carbon here in the middle represents that one. And this one on this one over here represents that carbon on the end. And you say, okay, great, I get that. What about the hydrogens? You assume the hydrogens are there. And it's enough to fulfill the octet rule for carbon. So you assume, and I'm going to draw them in, but we don't usually draw them in, that there are 3 hydrogens on that carbon there. We assume there are 2 hydrogens here on that carbon. And we assume that there are 3 hydrogens there on that carbon on the end. But we don't have to show them. I'll put those arrows back. Oops, lost everything. So we don't have to show all the hydrogens. Doesn't mean we'll never show them, but if they're kind of important, and for reactions a little bit later down the road, we don't have to, um, we don't always have to show the hydrogens. Now, here's the thing. This only applies to carbon and hydrogen. We show all other atoms. So for example, let's say we wanted to show the line angle formula for this compound. So again, we're just going to use these kind of zigzag lines for 3 carbons. So 1, 2, 3. And I have this OH group here. I'm going to draw that in specifically on that second carbon. So now if we kind of evaluate, let's just look right at this skeleton structure here, skeleton formula. And we know that that carbon on the end here has to have three hydrogens. Well, how do I know it has three hydrogens on it? Because I only see one bond to that carbon. So I know the other three bonds have to be occupied with hydrogens to fulfill the octet rule. This carbon right here has only one hydrogen on it because it's got one, two, three bonds already to it. That quote unquote missing fourth bond is occupied by a hydrogen. And then I know this carbon on the end here has three hydrogens. And so this type of notation is going to be used almost 100% of the time to represent organic molecules because organic molecules, and these are considered small, organic molecules are can be very large, upwards of hundreds of atoms in one single molecule, especially in biomolecules. And so this makes it a lot more convenient and a lot cleaner as well, where you don't have to show every carbon, you don't have to show every hydrogen. And if there's other atoms that are specifically there, like oxygen or nitrogen or phosphorus or halogens, we draw those in specifically. Now let me kind of show you another type of molecule here. We'll get into this in a couple of chapters, but let's look at what we call cyclic molecules, where the carbons are attached in a ring. And you can kind of see here how long this is taking me to draw all the carbons and all the hydrogens. So this is a series of 5 carbons. And I'll dive deeper into cyclic compounds a little bit later. But how do we show this as a line angle formula? Well, we just draw the geometric shape. It's a 5-membered ring. So I'm just going to draw a pentagon. And each vertex here, there's a carbon. And I assume, if I look around this carbon right here, I got a bond here and a bond here. I assume that the rest of the bonds are occupied with hydrogens. So there's 2 hydrogens on that one, 2 on this one, this one, and this one here. So I get the same amount of information from that skeleton formula as I do the Lewis structure. It just looks a lot cleaner because I don't have to show every single bond. So let's get some practice with this. All right, so here we're going to write this structural formula or condensed formula as a line angle formula. Now, this is kind of telling us what order the atoms should be in. I'm going to have 3 carbons in a row. If I were to leave it like this, I really want you to examine this here. If I were to leave it as it is, there should be 3 hydrogens on that carbon on the end, and there should be 2 hydrogens here. If I'm following the rules for drawing skeleton formulas. So that isn't correct. I should only have 2 hydrogens here and 1 hydrogen here. Now, you're looking at that and saying, you're violating the octet rule if those are the only things there. So how do I make this, follow the octet rule? I'm going to put a double bond right there. So when I draw the line angle formula, I still have my double bond, or, I have a double bond there. And now I assume, since there's already 4 valence electrons around that first carbon, I can only have 2 hydrogens here. And since there's 6 electrons around that carbon in the middle, I can only have 1 hydrogen on this carbon. And then this one on the end, since it's only got 2 bonding electrons there, everything else is filled in with hydrogen. So it will have 3 hydrogens there. Now let's do the same thing for this one. Now let's take a step back here and kind of apply something we did in the last lecture. Like, what does it mean? And I'm going to put parentheses here on this oxygen. What does that mean? Well, it means that this oxygen is supposed to be attached to only that carbon and that carbon only. But this one, this carbon's still attached to this one, and it's still attached to this. So if I'm going to draw those four carbons in a row, I'm going to start with my skeleton formula here, like this. All right, so this carbon right here is this on the end. This one here is supposed to be this one. This is this one, and this is that one there. Now, how do we deal with that oxygen? Well, if I'm going to start off here with a single bond, just put an O there. Okay, and I know the oxygen is going to have two lone pairs. So I'm kind of missing some stuff here. First of all, that oxygen is not happy. And if I were to leave it as is, it would imply that that's supposed to be a hydrogen there. I know from the structural, or I'm sorry, the condensed formula that there can't be a hydrogen there. So I'm going to fix that by making that a double bond. And now all the carbons are happy. All the oxygen is happy. They all fulfill the octet rule. And and all the hydrogens make sense as well. There's supposed to be three hydrogens here, no hydrogens on this one, two hydrogens here, and three hydrogens there. Now let's go backwards. Let's start with a skeleton formula and kind of go backwards to figure out, how many atoms there are. Let's do the molecular formula for this. So I'm going to take a look at this ring here. Wherever there's a vertex, and in the beginning, I recommend doing this. Let's just draw everything in. Here's a carbon. And according to the rules for drawing skeleton formulas, those carbons have enough hydrogens on them so that they fulfill the octet rule. So that means this carbon's got to have two. This carbon's got to have two. This one will have two. And this one will have two. I'm just going to put the lone pairs here on this oxygen. So now that kind of makes it a little bit more easy to come up with the molecular formula. I have four carbons. I got 8 hydrogens and then 1 oxygen. The kind of convention for drawing molecular formulas is you do carbon, then hydrogen, and then the other atoms like alphabetically. Okay, so this last example, we're looking at writing condensed formulas. So again, a condensed formula, just to show you an example, this problem that we did here kind of implies the orders the atoms should go in. It's a lot more information than a molecular formula. And so we're going to use those concepts to do this. So what we're going to do first is let's just look at the carbons here. At the end of the line, there's a carbon. So I'm going to number these so I can talk about them. 1, 2, 3, 4, 5, and 6. So if we look at carbon number 1, what is that? Well, I know that carbon number 1 has to be a CH3. Okay, because it's only got one bond to it. And so the rest of the bonds are going to be hydrogens. Now, if I look at carbon number 2 has this OH on it. And it's only got one hydrogen on it. We'll draw that in there. How do I know that? Because that carbon number 2 has 3 bonds to it already. So if I'm going to follow the octet rule, it can only have one more bond, and that bond is a hydrogen. Carbon 3 has 2 bonds to it, so I know it's got to be CH2. Carbon 4 has to be a CH2 because it's only got 2 bonds to it, so the other bonds are occupied by hydrogens. Carbon 5 is very similar to 2 because I got another group hanging off of it. And so it's going to have 1 hydrogen on it. And then 6 is like 1, where it's going to be a CH3. So when I do the condensed formula for this, I'm just going to go from left to right. CH3, and then CH. Now, to indicate that OH group is hanging off of the side, I can do one of two things. I can put it in parentheses like this, or I can actually like draw a bond like that. Either one's acceptable. And then I'm going to put CH2. There's carbon number 3. Here's carbon number 4. And then I'm going to put CH, because that's carbon 5, and then parentheses with the chlorine there. And again, that tells the reader that that chlorine is not part of the main carbon chain. It is attached only to that 5th carbon. And then put a CH3 there. So again, you could do it that way, or you can draw it off to the side, what we call a branch off of that main chain there. All right, and that's going to conclude what we're going to talk about with skeleton formulas. You're going to see me use this notation quite often. So what I would do is take some time, take a look at the problem set that I've posted, and start practice drawing line angle formulas, skeleton formulas, because this is something you're going to see over and over and over and over again. Probably won't get through one OChem lecture without me drawing a skeleton formula. So that is where we will conclude for today, or at least for this lecture. And when we come back, I'm going to go backwards a little bit and talk about this concept of constitutional isomers.